Hey there, welcome back to my YouTube channel. You are watching Build AI with Sandeep. Previously, in our last videos in our Transformer series, we have understood all the components inside the encoder and decoder block of Transformer architecture. Now, in today's video, we are going to understand a very important concept that is cross entropy. And after that, we will understand how the back propagation works and how in back propagation loss plays an important role. So let's quickly start our today's video. So first understand what is cross entropy. So it is a loss function. Loss function. In simple terms, if I want to write a definition, it tells us it tells us how wrong our predictions when the output are probabilities. So it is a number that tells us that how good our model is or how bad our model is. If the number is very low, then we consider that our model is performing very good. And if the number is very high, then we consider our model is performing good. So let's understand why we use cross entropy. This is a question. So let me tell you, in classification models, we have classes. So in output, we get the probabilities of each class, and we also know the actual class, the true class. Okay. So using this loss function, we are going to compare the actual and the predicted probabilities, and then we see that our model is good, our predictions are good or not. So imagine, let's take an example, and we have three classes: cat, dog, cow, and we have probabilities for cat word is zero point 0.1, zero point 0.8, zero point 0.1, and actual we know dog is the correct class, so we give dog a number 1 and other classes we put 0. Now we need a number. If that number is low value, then our predictions are good. High value predictions are bad. So in this case, what exactly we are trying to do? We are finding a loss function that tells us that okay, the prediction is very bad. You have to update your weights. So then we do back propagation, and in back propagation, this loss tells us will help us to understand which weight we should increase so that in the next pass we will get the good probability, the better probability. For example, in this case, dog is getting zero point 0.8 probability. It means 80% of the model is confident that the true class is dog. So it is a good model. It is considered as a good model. But what if this probability is around zero point 0.2? So in that case, this loss function will tell us that which weight we should update, and in the next pass, the dog probability should increase from zero point 0.2 to point close to 1. Okay, so the lesser the value is, the better our model, and the higher the value of loss, the bad is our model. The bad is our model. So now let's move forward. How do we compute this loss function? How? So the formula of the cross entropy loss function is basically minus y log of y cap. And this y cap, What is this y cap? Y cap is the probability of true class. True class. This is the formula. That's it. Now, one more thing I wanted to highlight, that this log is natural log. This is natural log, and we are not referring the log of 10. We are not referring this log. So let's consider two scenarios. Let's take an example, the same example, cat, dog, cow. But in this case, let's suppose we are running two model. So the first model is giving us the probability for the dog word is zero point 0.6, and in case 2 the second model is giving the probability for the dog word is zero point 0.1. Okay, now we have these two probabilities, but the case 2 is more worse. Case 2 is worse than case 1. Since in case 1 zero point 0.6 is closer to 1, there is a slight mistake. But in case 2, our model is confidently saying that only 10% we are predicting that that the next word is dog. So we need to we need to adjust our weights in such a way that in next pass this zero point 0.1 probability should increase and will be closer to 1, so that our model perform better. Now there is a one more question. Why log? Why log? There are two reasons. The first reason is strongly penalize confident wrong values probabilities. The second reason is stable gradient flow. I will talk about gradient after a while. So in the meantime, let's understand the first point, and let's take the same two cases and understand what will be the log value. For we know dog is true label, and model 1 is predicting zero point 0.6 probability for the dog word, and model 2 is predicting zero point 0.1. So in this case, what is the loss value? 0.6 is equal to minus of minus 0.51. So it is around 0.51. Now in this case, 0.1 minus log of 0.1, this will give us minus of minus 2.30, that is 2.30. Okay, so now our model can see there is a huge difference between the 0.51 to 2.30. There is a large gap. Our model can easily understand, okay, 2.30 is huge loss, and in we are going to adjust our weights using gradient and back propagation, and in the next pass this should be decreased for the dog word. Okay, so that is why we are using log. And let's take without log. Let's say we don't have log function, and we are using a simple error, that is 1 minus zero point 0.6 without log. We are calculating loss 1 minus zero point 0.6, and this is zero point 0.4, and in the other case 1 minus zero point 0.1, this is zero point 0.9. So zero point 0.4 and zero point 0.9 are closer to each other. These two are closer to each other. Our model might confuse that which one is better. So log strongly penalize the confidently wrong predictions. In this case, in model 2, only 10% it is predicting that dog is correct value, and it is confident, so it should be penalized more. It should be, our loss value should be greater in this case. So that is why log is penalizing this 10% low value, low probability to higher number, so that our model can easily understand that this loss is terrible and it should decrease. Okay, so that is why we are using log function, and again stable gradient flow. So for that, loss log curve graph, the graph of log like this. This is loss and this is probability. Now 0 and 1. Probability is always in the range of 0 and 1, and the graph of log is like this. So at probability 1 it is very minimum, but when the probability goes to near 0, the loss value will increase. You can see here in this curve, at this point loss value is very higher when the probability is closer to 0. So this curve so log is continuous and it is differentiable. That is why during training, our training process is very stable. There we will not face any exploding and vanishing gradient problem. And during back propagation, we have to do multiple differentiation, and we use chain rule, multiple derivative. So this log curve is differentiable at each point and it is continuous. There is a no break kind of this curve. Okay, so yeah, this is the concept. That is why we are using log in the in computing the cross entropy loss. So in summary, in summary, cross entropy tells us that how far our probability distribution to the in compared to the true labels. Okay, I hope the concept of loss is crystal clear now, and now we are heading toward the back propagation concept. Propagation. So you have heard this term many times throughout the Transformer series. So let me tell you, in every machine learning life cycle, in the training of ML models or in the training of deep learning models, as we are talking about deep learning model, so there are two paths. One is forward pass that we are seeing for many days. Forward pass, in forward pass we provide input, we generate tokens, embedding model, and model will give us logits. We apply softmax to get probabilities. Then we compute loss. So these all things we do in the forward pass, but in backward pass. The main aim of the back propagation or backward pass is to update the weights. And the back propagation starts from the loss. So loss is the starting step. Okay, then we compute gradients. After that we update weights. Why we are updating weights? Because in the next pass, in the next forward pass, the loss will be minimum. Okay, so this is the layman way to understand back propagation. Now we have computed loss, cross entropy loss. Now let's understand what is gradient and how do we update our weights. So I'm not going to derive the gradient formula, but there is a famous there is a famous simplification of this gradient formula, that is basically derivative of loss divided by Zi is equal to Pi minus Yi. So here Z is basically denoting logits, Pi is denoting predictions, prediction or probabilities, predicted probabilities, and this Yi is actual value. Okay, and this is basically 0 or 1 for the true label and 0 for the other classes. Okay, so this is the formula of gradient. And what exactly the gradient is doing? So gradient is telling us that in which direction we should move, in which gradient tells us the direction in which the weight updates, and our loss will decrease. So let's take an example again. So here let's take, we have again three classes: cat, dog, cow. Okay, and our model predictions are zero point 0.3, 0.6, 0.1. Okay, and the true class, actual class is dog. So one for dog and others for 0. So these are predicted probabilities, and these are actual value or actual classes, we can say classes. Okay, so now gradient is basically predicted probability minus actual classes. So now in this case, zero point 0.3 plus zero point 0.3, our gradient value, okay, plus 3, and this is minus zero point 0.4, and this is zero point 0.1. Okay, so the sign of gradient is telling us that we have to decrease this, we have to increase this value. Since it is minus zero point 0.4, so in the next pass we have to increase this gradient to close to 0, and this is also we need to decrease. Plus sign, it will decrease in the next pass, and the minus sign, it will increase in the next pass. Okay, so that is all about gradient. Gradient basically tells us that in which direction we should move, and we use a famous optimization technique, that is gradient descent. And this gradient is basically lies at these points in the start, and here there is a global minima. We have to adjust our weights in such a way that our loss will come at this place where global minima is present. That's it. And we understand about the gradient, that gradient is telling us the direction. Now let me tell you the formula to update the weights. W new is equal to W old minus learning rate times derivative of loss divided by derivative of weight. Now this is our gradient. This is our gradient. And we can also write derivative of z divided by derivative of weight. We can also write this, since it got cancelled out. This is the same term. So if I tell you that this term we already know, predicted minus y actual, prediction minus y actual. Okay, this term, the formula of this term we already know, and I'm saying what this is. This is basically input value. Okay, so So you are confusing right now that okay Sandeep, why are you saying that this is an input value? So I want you to take back to the transformer architecture. In the decoder, in the decoder, we write again decoder, we pass input from here and we get this output, and we apply linear layer. Linear layer will give us logits, Z eyes. Okay, so the output vector at this point are the input of the linear layer. Okay, and I am referring the input values to this place. Why? Because what is Z? The logits. What is Z? What we have done inside the linear layer? We basically hidden state, we did a dot product. Hidden state multiplied by weight plus bias. And this hidden state are basically these output vectors. Okay, and we multiply with weights and bias, and this is basically our Z. And when we apply derivative with respect to weight, then this W got cancelled out. When we apply derivative, the hidden state, or we can say, input value of the linear layer, and bias 0, because it is a constant value. So that's why I'm saying dz by dw is the input value. Now our weight update formula will become w new is equal to w old minus learning rate times prediction minus actual multiply by input value. And it is same for all the components. It is same for the our weights will update in the feed forward layer, cross attention, mass self attention, wherever we have used weights and biases. The process is same for all the places, and this is the exact formula we are using to update our weights. And what is this learning rate? It controls the speed. It controls, so basically learning rate controls the speed, how fast we are going to converge to the local minima, how fast we want to converge or met to the local minima. So that is how we update our weights inside the inside our transformer model. So now we have understood about cross attention and the back propagation. Now I want to congratulate if you all are with me throughout the Transformer series. We have just completed our Transformer series, and in the next video, I will come up with a very interesting video, that is Transformers to LLM. If we have the Transformer, then why LLM came into picture? How LLM came into picture? And one last thing about the Transformer series, one last thing that I wanted to tell you, that we have understood encoder block and decoder block, and we connect it to the cross attention, and we pass input here, we pass input here, we get the output next token words. First we use, first we give start special tokens, and it will give us the uh, first next token here. And so the main important thing is that in original research paper there are six encoder blocks and six decoder blocks. So it is like this: one decoder block, two decoder block. So let me write neatly: one encoder block, second encoder, and it will goes to six encoder. Okay, this is our input. Similarly, decoder 1, decoder 2, and decoder 6. These are connected, and here, and it will give us this and this. So you can now imagine that how many parameters we have in the transformer model. There are thousands of parameters, thousands of weights and biases, and this is a huge architecture. So if we have this architecture, I'm questioning that what is the use of LLM? Why LLM came into picture? If we have the transformer architecture with so many parameters and we can train it on huge data, pass, we can process our sequence parallelly throughout the encoder and decoder block. And so one more thing I want to tell you that the transformer based models are not learning on sequences. They are learning token by token. Okay. Whether we are passing a whole sequence into the encoder and decoder is we are feeding a whole sequence to our model, but our model is not understanding sequence to sequence. It is understanding, it is learning token to token. Its main goal is to predict next token. That's it. That is the main idea. Okay, so that's all for today, and I will meet you in my next video. Thanks for watching, and if this video helped, then please do like, share, and subscribe to my YouTube channel. I know you all are watching my videos, but not subscribing. So please do subscribe. It gives me some motivation so that in future I will come up with many interesting AI videos. Thanks for watching.